We are for chapter 3. So this is about modeling for pharmacokinetics, and the chapter begins with this quote: "All models are wrong, but some are useful." And I really like that. Uh, just to recap that, I think we all know that these models of the atom are wrong, but it's not like an atom looks exactly like that. And our latest one is not like we think it's that. But it gives us something to relate to and kind of a frame to work our minds around. Um, yeah, same thing is going to happen here. So there's something called non-compartmental analysis, or NCA, and basically you're just assuming that the whole body is blood, and that's because you give a person a drug or an animal a drug, and then you check the blood level and assume everything is blood. So let's just look here. We've got the concentration on the left and then the time. And if you give a drug, it starts at 0, so that was probably given orally or some other way, and it decreases over time. It increases and decreases, makes sense. If you plot that as a log function, it looks like a straight line. I want to point out that actually this drug is getting cleared faster and faster. So if you look on the left, it goes from 30 to 20 in perhaps 4 hours. Then going from 20 to 10, it takes about twice as long. And then 10 to 0, it's even, again, twice as long as that. So the reason that the drug concentration is changing at sort of just different rates is because the body has access to only so much of itself. So basically, think of the kidneys. The kidneys are going to clear whatever they see, let's say 100%. But as they clear it, the odds of this drug going to the kidneys decreases. So the less there is, the slower it's going to get cleared. This is the same as radioactivity or radioactive decay, and then if you have a smaller sample of radioactive material, it's going to decay like slower. There's less molecules that will decay because there's just less molecules. Okay. Now there's something called PBPK, and that's physiologically based pharmacokinetics. What that is trying to say is we're not going to assume everything is blood, but we're going to try to account for every single type of tissue and the concentration in each of those tissues. So we know what our blood concentration is, but based on what we know about the drug, how much is in the liver, how much is in the gut, how much is in bone, and there's, their rates, obviously, that those change by, and those are all based on concentrations, but you can have often 14 different compartments. So we'll talk about how the physiochemical properties affect that. Basically, because there's so many models for pharmacokinetics, you actually want to find the model that's appropriate for the drug you're studying. So that's called fit for purpose. Now, that's kind of an interesting concept. Like if you were studying the atom, I guess you could do that. You could pick a model based on what you're studying, but normally we don't talk about just changing models all the time. But we do for pharmacokinetics, and that's called fit for purpose. Okay, the NCA is often used because it describes the data, and so that's its job. So it's not like we do the PBPK for everything, or we almost do it for nothing, because first off, that's specialists that do that, special software and licenses and all that. Anyway, so with this NCA, there is an assumption, and that is that the distribution occurs instantaneously, and that it's all one compartment, and that the whole compartment is what you're sampling, which is blood. So with that, let's talk about what's really going on. So in reality, there's some water-based compartments, and the water-based compartments, um, there's the extracellular fluid space. So that extracellular space is going to be anything outside of a cell. So that's your blood, but also the kind of the fluid in between tissues that's not inside a cell. If you add all that up, that's about 14 liters. And we know that, but an example is like inulin. Inulin will go to wherever there's water, can go to that, but it cannot enter into membranes, enter into cells. So it's very nice. Um, Now it gets tricky because you'll often hear something called plasma proteins. Plasma makes it sound like they're in the blood, and they probably are in slightly higher concentrations, but the plasma proteins go throughout the whole ECF. And they're often, if you're measuring a drug that's protein bound, you're often going to get that bound part measured as well. So it just makes a difference. We'll show you in the next slide. But here's an example. Um, the most common protein is albumin, which I should have labeled that. That's probably representing albumin. Albumin is negatively charged. So if you hyperventilate, and you'll actually increase protein binding because you're blowing off your acid, or you're blowing off H positive, which means you're uncovering more negative charges, which means you can have increased binding. And if you don't breathe as much, or if because then you're in respiratory failure, your pH is going to drop, and so now you have less binding. Anyway, I just think that's interesting. But yeah, plasma proteins, 9 times out of 10, it's talking about albumin and binding to albumin. Okay, so in the extracellular space, there's also intravascular space, which is just how much blood do you have, and that's about 5 liters, 4 to 5 liters a gallon, not much. Then there's the intracellular fluid, so that's what's inside all of the cells, and I guess we kind of know that probably by several ways, but we can calculate the total body water. So there's some drugs like caffeine and urea that can go through all water, and also can go freely through membranes. So because we know the total body water, we can calculate the intracellular fluid. But just so you know, the average human size is 66 liters. So we're saying most everything in the human is water based. And these were all like hydrophilic molecules. We'll talk about that more later. But okay, so thyroxine is a protein bound uh, molecule. It's like Synthroid. A lot of people are on Synthroid or levothyroxine, but thyroxine is protein bound. Because of that, the um, the proteins stay in the extracellular fluid. So in this case, maybe thyroxine can go into cells, but it's not going to because it's bound to the protein. And so its volume of distribution is going to be lower, like maybe 14 liters. Um, Now, theophylline, which is like caffeine in structure, is only like 40% bound to plasma proteins, which means if it can, like caffeine, you would think it could go throughout the whole body and it would have a 50-liter um, volume of distribution, but instead it kind of favors the extracellular fluid. Um, oh, so I think that should. So it favors the extracellular fluid. So the point is, it's not total body water, and it's not just ECF. It's sort of in between those. The fact that it's also 35 and the ICF is 35 is just a coincidence. So that's what I was frustrated about. Okay, hopefully that makes sense. There's just going to be a greater proportion in the extracellular fluid because there's the 40%, but then there's also the 60%, and then that 60% that's free in the plasma is going to be the equal concentration of what's in the ICF. Hope that makes sense. Okay, now just as an example, a lot of proteins, everyone's talking about monoclonal antibodies, so they actually just stay in the intravascular space, and so their volume of distribution is like 4 liters. And the body actually keeps those proteins in. I looked up another protein, and its volume of distribution was 7. That's one that everyone's talking about right now, the Wegovy or Ozempic. But that brings me to the point we don't always know what the volume of distribution means physiologically. So I gave some pretty obvious cases of simple molecules, but in reality, does that 7 liters mean that it's let's say sequestered by the liver a little bit, and then the rest stays in the blood, or does it mean that it's protein bound mostly, and that it's you just don't know. And actually, semaglutide is protein bound. That's how they got such a long half-life. So I was actually really surprised to see it was 7 liters. Yeah, I was expecting a lower one. Anyway, the point is we don't always know what it means. Let's move on here, and it'll be more. So talking about the opposite types of molecules, so that's like super hydrophobic molecules, such as like amiodarone or vitamin D or steroids. They just distribute through all the fat, so they want to go to the fat. So what you could do, you could measure that kind of preference by what's called this octanol and water partition coefficient, and basically you just have octanol and water and put the drug in the solution, and then I guess mix it up and measure it in the 2 different solutions after it separates, and then you'll know kind of the ratio there. So it's literally that simple. And if the coefficient is high, such as for digoxin, that means it's a drug that prefers to be an octanol. So it's lipophilic. Now, just so you know, because of the changing pHs, that's going to sometimes change the charge of the molecule, and so that can sometimes affect the, if it's charged, it's obviously going to be more hydrophilic. So that's what this D octanol coefficient is. It's sort of an adjusted partition coefficient for the what can I think? But the pKa and the pH. It compares like how strong of an acid that is, and it accounts for how tightly the hydrogen is being bound. So, and it's trying to calculate or compensate for both forms of the molecule. So sometimes it's exactly the same and sometimes it's not. All right. Now let's move on to digoxin. So for digoxin, the partition coefficient is about 20. So that means for every 1 molecule in water, there's 20 in fat. So if we're measuring, remember we're measuring blood, and we're assuming everything is blood. So to dissolve the same amount of digoxin that's in fat in blood is going to take a lot more blood. So that's why we get 536. I already told you the human body is only 66 liters or 70 liters maybe. So typically a volume of distribution this high means it's something that doesn't like to be in the water. It's not soluble in water. It doesn't like to be in the blood. And that's what digoxin is. It likes to be in fat. Same with steroids, vitamin D, which is a steroid also. Just things I can think of right now. That's why vitamin D takes so long to load also. This huge reservoir. All right, hope that makes sense. Often, we don't know what the volume of distribution actually means from a physiologic perspective. It's helpful to think about it, and but it helps us with calculations, and we're trying to the exposure. So there's dosing, and then there's exposure, And so we're trying to find that out. So let's talk about the volume of distribution again. Let's see, change in volume of distribution does not affect the average concentration or AUC, assuming the clearance is the same. Okay, so once you have volume of distribution, now you can understand clearance. Clearance is going to be in volume per time. So it might be, let's say, 2 liters an hour. What that means is if you had a volume distribution of 4, it's going to clear 2 liters an hour, right? So that does not mean it's going to clear everything in 2 hours, because as you clear 2 liters, the drug is going to spread out again, and you're going to clear another 2 liters, and it'll spread out again, sort of. So, but if you were to double the volume of distribution, somehow magically have become like twice as large, assuming the clearance stays the same, it's still 2 liters an hour, the clearance is going to take a lot longer. So your peak concentration is never going to get as high in the 8 liters, but it's going to take much longer. So your average concentration is the same. Sometimes that's all you care about is what's the average concentration, or sometimes you care about like the time above a certain threshold. Just depends on what your drug does and how it works. Yeah. Okay, then VDSS, so that's the volume of distribution at steady state. So that's going to be the thing that's the smallest of all the VDs, based on how you calculate it, because when you're at steady state, there's not a lot of intercompartmental shifting, and so the volume tends to stay in, or the medicine tends to stay in the blood, so your volume of distribution is going to seem smaller. All right, so this is the first slide, the NCA. Hope that makes sense. It's kind of misleading. Well, all right. Now we'll talk about the intercompartmental clearance. I'm telling you that to start introducing things that are more than just single compartment. So you could actually have like a 2 or 3 compartment clearance model. So that's kind of in between the PBPK and the NCA. So basically, this circle with the VC, that would be the blood essentially, and it gets cleared through, we'll say, the kidneys and the liver, but also there's capillaries and cell membranes and splanchnic tissues, which is going to be like the gut, somatic tissues, which is like musculoskeletal. So you're kind of treating them like they're at their own compartment. What does that look like? So it looks like something like this. It always happens, but you want your model to account for it when you get something like this. So notice that there's a log scale on the y-axis, and so the first time we saw the log scale, it was just a straight line, essentially. In this case, you get the medicine, and it looks like you got an IV injection, and then it drops off very quickly, and then there's almost this complete change in rate, and that's the beta slope there. What's happening here is you have distribution. So the alpha slope is there's a lot of distribution. There's just a time where it's really distributing quickly. There's, the injection, and it's getting cleared by the kidneys, but it's also, distributing, say, to bone because that's empty. All right. Once everything's distributed, it's going to be a constant GK. And so you can tell when you're in distribution phase based on multiple slopes. So for instance, the distribution phase here was maybe 3 hours. Not all drugs would need that, and so you might not have much of a distribution phase. On the other hand, distribution phase might be very long compared to the half-life, or compared to the elimination. So hopefully that makes sense. Now you're going to get these, your model is just going to look like that C equals A prime e to the minus alpha t plus b prime over there on the left. So basically, you're adding those together, and if you added these two straight lines together, you would get a line that approximates the actual concentration. All right. So this might be too deep, but sometimes you can have a prolonged distribution phase. I'll just tell you what is happening with this, and hopefully you make sense of it in some way that's meaningful to you. So this is gentamicin. Gentamicin is very nephrotoxic, and also it goes to the kidneys. And someone showed that, like with tissue biopsy, that it really just prefers to stay in the kidney. So there are two patients. One had nephrotoxicity, which was the patient with the filled-in holes, and then we'll say the normal patient, that had pharmacokinetics like we'd expect would be the patient with the donut holes. So what you see here, once again, look at the log scale. So you can see there is a very long distribution phase. Let's look at we'll say the normal patient first. It's almost like 2 days of distribution, and then your elimination levels out. Well, what's happening is the kidney is clearing it, but actually the tissue of the kidney is absorbing it, and that's why it's nephrotoxic. And it gets saturated at about 3 days. Now, that's fine, and we can model that based on whatever goals we want. Maybe we wanted gentamicin above a certain threshold, so that we were treating an ear infection, so that the concentration in the ear is such and such. Okay, what happened to the other guy? So the other guy had nephrotoxicity, so he got a little gentamicin, and then his kidneys shut down. So because of that, it no longer distributed. There was no kidney for it to distribute to, because of impaired blood flow and things like that. So because of that, the distribution phase in the top patient, basically was only like a day. These patients got the exact same starting dose, the exact same peak, and so because it's no longer distributing into the kidney, now it's going to just go through normal elimination, which, because the kidney's out, I assume that's getting eliminated through the liver. But notice that the slope of the elimination phase is basically the same. So that's a way to think of that. So flip-flop kinetics sounds pretty cool, but I guess it really just means, hey, you might want to consider a 2-compartment model, so not an NCA. And you're going to be able to tell that because when you put a log, when you graph your concentration with a log, there'll be multiple slopes. All right, I guess that's it. Well, all right, I hope the modeling makes sense, and we'll see you next time.